Today we're going to dive a little deeper into theory of plate tectonics. We're going to review all the different kinds of boundaries and what happens when those plates come together in different ways. Make sure you have your plate tectonics notes out in front of you and get ready to write or highlight. The Earth's lithosphere is actually divided into plates or pieces. Okay, sort of like puzzle pieces, like Pangea, except these are actually the lithosphere or the crust broken up into different pieces. And those are constantly moving on our asthenosphere. It's a little bit like if you were in a raft and you were in the pool. The raft would be a plate, one of our lithospheric plates, and the water would be our asthenosphere. As the water moved, you would also move. And our major plates are always moving in one direction or the other. You can see in the picture how all the plates connect. All these plates put together make our Earth. There are some major plates and there are some minor plates. This is a great illustration of some of the major and minor plates. You can see that we live on the North American plate. It extends into the Atlantic Ocean. There's an African plate, a Eurasian plate, an Australian plate, the Antarctic plate, Pacific plate. Those are some of the bigger, we would call major plates. But there's also some very small plates, the Caribbean plates, the Arabian plate. Some of those are very small, but we have to have them all put together like one big puzzle to have our Earth. Because remember, all of these put together make our lithosphere. So thinking back on the picture we just saw, we know all the plates touch. Well, they can touch and move in different ways. The first thing we're going to talk about is what happens when they meet. They form what's called a boundary. So when two plates come together, there is a boundary. And there are three types of boundaries we're going to talk about: convergent, divergent, and transform. Different things happen at each one of these boundaries. The first type of boundary we're going to explore is our convergent boundary. Convergent boundaries push together. They collide or they crash. We can have ocean crashing with ocean. We can have ocean colliding with continent, or we can have continent colliding with continent. So that would be a continental plate and a continental plate, an oceanic plate and a continental plate, an oceanic and an oceanic. And depending on which type of lithospheric plate is converging, it's going to create different things. When an oceanic and an oceanic plate come together, something is going to happen, and it's known as subduction. That literally means that the crust is sinking. When one oceanic plate meets the other oceanic plate, one is going to be a little more dense, and we know more dense sinks. So it's going to subduct or sink under the other oceanic plate. Whenever there is subduction, it's going to create a trench and a volcano where that subduction takes place. The same thing happens with oceanic and continental. We know oceanic is much more dense than continental. So when the oceanic plate converges, collides, or crashes with our continental lithospheric plate, the oceanic crust is going to subduct or sink under the continental crust. That subduction is also going to create a trench and a volcano. And finally, we have continental plates and continental plates meeting. These are going to be closer in density than an oceanic and a continental. So what's going to happen when they collide is they're going to collide and they're going to move up. Nothing's going to sink, and that's going to form our mountains and our mountain chains. Again, a very important term to remember in convergent boundaries is the term subduction. Subduction means that the crust is sinking. It's actually sinking back into the asthenosphere and it's going to melt. The first type of convergent boundary we're going to talk about is where oceanic crust meets oceanic crust. You can see this oceanic crust on the left is more dense, so it's going to subduct or sink under the oceanic crust on the right. As it sinks, it's going to start melting and it's going to become molten rock in the asthenosphere. It's also going to create a trench, which is a large V shape that goes way down into the ocean. We'll talk more about trenches when we get further on in our study. It's also going to create a volcano or a volcanic island arch, because that magma not only is going to be created when it subducts, but it's also going to be pushed up right there into the oceanic crust and create our mountain. The second convergent boundary collision is where an oceanic crust crashes into a continental crust. The oceanic plate, we know, is going to be denser, more dense, because we've got that ocean pushing down on it. So it's going to subduct or sink below the continental plate, which is less dense. Again, it's going to go down. It's going to start melting into molten rock again. It's going to create our trench because it's subducting. And some of that molten rock is going to ooze up and it's going to create our volcano. Our final convergent boundary collision is where a continental plate collides or crashes with another continental plate. When they come together, neither one is super dense, so they're going to crash and it's going to create a rise in the earth, which is going to create our mountains and our mountain chains. The Himalayas are a really good example of where a continental plate collided and created a mountain chain. The next type of boundary we're going to talk about is a divergent boundary. Divergent boundaries are when two plates come together, but they're pulling apart. Okay, we know a boundary is when they're touching. So these two plates that are touching are going to start pulling apart. And the reason they're going to pull apart is because the molten rock is going to be pushing up from the mantle, creating this little crack. And when it gets up onto the ocean floor, it's going to harden because it's cooler up there. And it's going to create a mid-ocean ridge. So again, they're going to be pulling apart, causing that mid-ocean ridge. And that seafloor spreading is what actually happens, because remember that when the molten rock comes up, it's got to make room so the crust moves apart. It allows that molten rock to come in and it hardens. Then it's going to repeat. Later on, that same molten rock is going to ooze up. It's going to create that crack. It's going to harden, and our crust is going to have to move out of the way. It's going to spread out, allowing more crust to be formed. It's specifically at our divergent boundaries where mid-ocean ridges are formed. Mid-ocean ridges are nothing more than an underwater mountain chain that runs through the Earth's basins. That means the ocean floors. As magma from the mantle rises at a divergent boundary, it's going to push up. It's going to solidify. That means it's going to get harder because it's colder up here than it is in the mantle. Okay, that older crust is going to get pushed away. It's going to spread apart, allowing that magma to form new crust. And again, that's going to repeat over and over again. And every time that new magma squeezes up, the ocean crust has to separate or spread out some more making room for that new crust. The last type of boundary we're going to talk about is a transform boundary. This is probably the one that you know the most about. It's when the plates slide past each other in a side-to-side motion. So they're moving in opposite directions. This is going to cause an earthquake. So if you think about it, it's these two plates rubbing tightly against each other. It's like if you took two really hard cookies, pressed them against each other, and moved them in opposite directions. You're going to have some crumbling going on there. And that's the same thing with these transform boundaries. As they move in the opposite direction, one plate is scraping against another plate. So it's going to create an earthquake or a tremble or motion in the earth. You may be asking, well, what makes it all happen? Why are these plates moving? Well, we learned a while ago that in the asthenosphere, that melted, ooey gooey, semi-solid, molten rock is always moving. Well, now we're going to learn about why it's moving. And the reason it's moving is convection currents. So we've got that molten lava that's really hot, but we know the further we go down, the hotter it gets. So we've got that really hot melted rock at the bottom, and we know hot things are less dense, so they begin to rise. But we also know as they rise and get closer to the lithosphere, it's going to get cooler. So when it gets cooler, it's going to be more dense. And when it's more dense, we know it sinks. So it's going to begin sinking back down to the mantle. And we know as we go down, temperature increases. So it's going to get less dense. As it gets hot, it's going to start to rise again. And this is a continuing motion. And as this continuing convection is going on in our mantle or asthenosphere, it's going to make the asthenosphere keep moving, and the lithospheric plates are going to be floating on top of that, and they're going to be moving around with the motion of this convection current. So this is really the driving force behind all our plate movement. So here's a good example of the hot molten rock coming from the core and rising. Some of it is going to escape, and it's going to cause the seafloor spreading. Some is going to cool, and it's going to fall back into the mantle. It's going to get hot again and rise. Some of it's going to squeeze through. It's going to cause the seafloor to spread. It's going to create a mid-ocean ridge. And some of it's going to cool, and it's going to fall back into the mantle where it will get hot again and rise. And again, this is a continual process over and over again, and that is what's making our plates move. So you can follow along with the directional arrows, and I want you to think about where is the most dense, where is the least dense, where is it rising, where is it falling. So I want you to think about that as you look at this. And I want you to think about how all this movement is making our continents slowly move over time as these plates move. This is a great example of how things are moving.